So that we have about 20.
Okay, let's continue. Example number 6. Determine whether B is the linear combination of the column A, where we have the A there and the B. So in this case, so this is actually like coefficient matrix, the A, and then so in this case, this is like the vector A1, or we can use V1, V2, V3 here. So those are like the vectors. So when you bring them together, then we form a matrix A. Matrix A. Okay, so we need to check whether this B here is a linear combination of columns in A, the linear combination. So in this case, we need to write this in augmented matrix form. So solution. So we write this one in augmented matrix form. Augmented matrix form. And then now we reduce. So we reduce this matrix. So we want to see whether this final matrix is consistent. It's consistent. So to reduce this, then of course they have reduced the second entry in the first entry in the second row, and then so we reduce the last one. So to get the new R3, then it is R3 minus R1. R3 minus R1. So here we get 1, -2, -6, 11, and then 0, 3, 7, and then -5, and then this is 0, -2, -2 is 0, 5, -6 is 11, and then 9 minus 5 is minus what? Is minus 2. Minus 2. So in this case, we can see that it has already been introduced. So we have the pivot position here. All those are pivot position. Now, therefore, if the last row is not particular, then it means then this matrix is what? So Therefore, the last row is not contradictory. And therefore, it is consistent. So if it is consistent, then it means that B is a linear combination of columns in A. B is a linear combination of columns in A. Okay. That's it. Just check whether the last row is contradictory or not. Okay. Example number 7. For what values of the parameter h does y lie in span V1, V2, where V1 equals to 1, 0, -2, V2 equals to -3, 1, and 8, and then y equals to h -5 and -3, h -5. So for what values of the parameter h, that's why I like in the span of that. So the span is said is a collection of vectors, which are linear combination. Okay, so this case, then we need to know the values of h that can make this to be consistent. That can make this be consistent. So then we need to write this matrix in augmented matrix form. Then now we reduce it. Then we reduce. So to reduce this, then they have already reduced for you the second entry there. So to get the new R3, then it is R3 plus 2 R1. R3 plus 2 R1. Okay, so 1, -3, H, and then we have 0, 1, -5. Then we have 0 there. 8 minus 3 is 11. Sorry, 8 plus 3 is 5. So it will now be 5. And then minus 3 plus, so minus 3 plus 2H. 3 plus 2H. Good.
On the bottom row, shouldn't it be a 2 instead of the 5 because you're doing 2 -3?
So this is, oh, shouldn't. So this one should be 2. Okay. So we need to reduce this. So the 2 here. So to get the new R3, then it is R3 minus 2 R2 minus 2 R2. So we have 1, -3, and then H. And then we have a 0 here, 1, -5. And then we have 0. We have 0. And then we have, in this case, it is -3 plus 2H. minus what? Plus now 10. So it will be 2h plus 7. So 2h plus 7. Plus 7. Now, so for what values of the parameter h does y lie in this part of that, where that is v1, v2, v3? So what can we see from here? Now, for this one to be consistent, if we leave it like that or make the value of h to be, let's say to be 1, then it becomes what? Contradictory, right? So it becomes contradictory. So if we have a value here and all these are zeros, then it becomes contradictory. Now, for this one to not be contradictory, then this should be what? 0. So that should be 0. So we can say the vectors equation, the vector equation, x1 b1 plus x2 b2 equals to y is consistent if and only if 2h plus 7 equals to 0. If and only if 2h plus 7 equals to 0. So our h should be equals to -7/2. So therefore, when h equals to -7/2, the vector y is in span v1, v2. Any question after that? Any question? Okay. Now let's now come to the next section. The next section, which is 1.4, and then this is matrix equation. This is matrix equation. Okay, so in this, then we can start from the first one, where we are going to look at the matrix vector product. The matrix vector product. So we're going to multiply matrix vector. So let's start by the definition 1.1. So definition. So if we let A to be equals to A1, A2, AN, if those are vectors, A is a matrix, and that matrix has the vectors, the column vectors, A1, A2 to AN. B, an M by N matrix, where the vectors A1, A2, AN are elements of Rn. Elements of Rn, which we can say are vectors in Rn, and let's x to be equals to x1, x2, xn be vectors, vector, where x is a vector in also Rn. The product of the matrix A and the vector X is defined by AX, which is equals to A1, A2, and these are vectors, AN multiplied by X1, X2, Xn, which is the same as X1, A1 plus X2, A2 plus Xn plus Xn. Now, here we are multiplying, so if you multiply matrix, so this is not a matrix, this is the vector X. So when we multiply this, that, and that, then we form that equation. We form that equation. So the matrix vector product AX is defined only if the number of columns in A is equal to number of entries in X. In this case, AX is a vector in Rm. AX is a vector. So here, for this matrix to multiply with the vector, so the number of columns in H, these columns here, should be equal to the number of entries here for that to multiply. So they should be equal. If these are n columns, then the entries, or yeah, the entries here should be what? So the product of this product here is now in Rm, is now in Rm. Because when you multiply this and that and that, then what we get when you multiply these in Rm. So we will see on how we come to that. So these are actually the elements.
Shouldn't vector sign be over the A or the X?
No, over the X. So A is the matrix.
Okay.
So this one is the
very.
What is that?
Here on this side of the equation. On the right
This
side.
one?
Yeah, it's that.
So these are coefficients. X1s are what we are going to solve. We are actually looking for X1, X2, and X. So these are like coefficients. So finally we'll get a solution of X1, X2, and X3. So all of these are vector. It's a vector X. It's a vector X. So A1 are the columns. So this is a column, this is a column, and that one. Okay, now let's look at the first example. Example number 1. Compute the following matrix vector products. if it is defined. If it is defined. So if we have the first one here, we have 2, 4, -1, 3, 2, -2, -1, 8, and 4. And this is 0, -1, and 3. And then we have -1, 0, and 2. -1, 0, and 2. So this is the matrix there. And this is now the vector X. So these are like now A1, A2, and this is A3, and this is now the vector X. Now, when we now multiply A and B, then that is now the matrix multiplied by 1. So for this to multiply, that means that the number of columns here should be equal to the number of entries. The number of entries. The number of columns here are what? 1, 2, 3. Entries here are 1, 2. So they should be equal for this to multiply. Now, to multiply this, then this is equals to what? So it is the same as now, if you still remember, looking at this up here, so it is the same as multiplying. So if we take this one as x1, this is x2, and this one is now x3. Then therefore, this is equals to x1, which is -1, multiply this by 2, 3, -1, and 0, plus this is 0, multiply this by 4, 2, 8, -1, and then finally plus 2, multiply that by -1, -2, 4, and 3. So it is the same. So taking x1 multiplied by the first column, x0 multiplied by now. So here now, what do you get? So we can now distribute, if you still remember, when we multiplying a scalar by a vector, then we take this one inside here, so we get -2, -3, 1, and 0, and then plus this will now be 0 vector, right? 0, 0, 0, 0, and then plus -2, -4, 8, and then 6. Now, then we can do, we can now add that. So finally, what do you get? -2 -2 plus 0 -2 is -4. -3 plus 0 -4 -3 -7, and then 1 plus 8 is 9, and then 0 plus 6 is 6. And that is it. So that is the easiest way of multiplying the matrix. Any question up to that? Okay. Example number 2, number B. If we have this 2, 4, -1, 8, 2, -2, 1, 8, and 4, 0, -1, 3. Multiply this by -1, 0, 2, and 3. So the first of all, we need to look at the number of columns and the number of entries. Are they equal? So they are not equal. So therefore, the solution of this is that the number of columns in the matrix is not equal to the number of entries in the vector. So this matrix vector product is undefined. Is undefined. Is undefined. Any question up to there? Okay, now let's come to the next part here, 1.2. This is the raw vector rule. The raw vector rule. So when we multiply the matrix vector, so there is a row vector, the row vector. So we need to see how we can multiply the rows by that vector. So the row here is the row here. So let's see. We can write the I entry in AX. The I entry in AX is given by AI1 X1 plus AI2 X2 plus AIN XN, where A equals to A11, A12, A1N, AI1, AI2, AIN, and this one is AM1, AM2, AMN, and X equals to X1, X2, and there is XN. Now here, what you can see is to get now the I entry here, then we are multiplying the first entry here, let's say A11. So if we put I to be 1 in all this, then the product here, the first entry is A11 multiplied by X1, A12 multiplied by X2, A13 multiplied by X3, A1N multiplied by Xn. If I is equals to 2, then it will be now A21 multiplied by X1, A22 multiplied by X2, A23, like that, up to the last one. So that is the row vector rule. So A1, so I can be any value, I can be 1 up to 10. So for example, so let's look at example number 2 here. Computes the matrix vector product of 8, 3, -4, 5, 1, and 2. Multiply this by 1, 2, and 3. 1, 2, and 3. So multiplying this. So first of all, you check whether columns are equal to entries. So which are equal. So the product is defined. So to get this, then we now use the row vector rule. So we multiply 8 by x1 plus 3 by x2. So it is 8 multiplied by 1 plus 3 multiplied by 2 plus -4 multiplied by 3. The next one yes. So the next one will be what? 5 multiplied by 1 plus 1 multiplied by 2 plus 2 multiplied by 3 plus 2 multiplied. So as you can see, this is from Rn. So these are Rns, right? So what we form here, which is Ax, R, M. So those are actually, so here what we get here is equals to 2 and 13 there. So here is A, and this one is X. So what we get here is Ax, Ax, Ax. Now, this is an M by N matrix. And this is the entries here are in Rn. So the entries here, which is A1 to A3 in this case, A1, A2, and A3 are elements of, actually, in this case, they are what? They are 3 elements in R3. Elements in R3. Now, what we get in the product here are 2 entries here. So there are 2 of them. So these are elements in R1, R2. So those are elements in R2. So what is this matrix here? This is a what? A 2 by what? A 2 by 3 matrix, right? Mn. M is the number of rows, and the n is the number of columns. The number of columns. So M, and then this n. So Mn. So they are in R3. So they are in R3. R3, this one. So they are in R3. The product is in R what? R2, like what we just wrote here. So this case, Ax is the vector in what? In Rm. And M are the number of rows. M are the number of rows. N here are the number of columns. N are the number of columns. Any question? Any question? Okay, now let's come to the next section, which is 1.3. And these are properties of the matrix. vector product. The matrix vector product. Now, if A is an M by N matrix, U and V, the vectors U and V are elements of Rn, and C is an element of real number, which is a scalar, then when we multiply A by vector U plus V, this is the same as AU plus AV. And A multiplies CU is the same as C A U, same as A. So we can add the two vectors and then multiply by the matrix, or we can distribute the matrix here. This matrix multiplied by the vector U plus the A. So they add. You have the scalar here, and then you have the vector, so we can multiply the scalar by the vector, and then that's how we multiply the matrix. Or we can multiply the matrix here by the vector and the scale. So let's prove this. Let's prove the two of them. So let's prove. Now, if we write A to be equals to A1, A2, AN, and U to be equals to U1, U2, up to UN, and V to be equals to V1, V2, up to Vn. Then U plus V equals to U1, U2, UN, or U plus V. So U plus V is the vector which is formed by adding U1 plus V1. So U1 plus V1. The second one would be U2 plus V2. Third one would be U3 plus V3. And then finally, the last one is UN plus Vn. So U plus V is that. So U1 like that. Now, when we now have C and U, then this is similar to CU1, CU2, up to CUN, CUN. So A multiplied by U plus V is now similar to U1 plus V1 multiplied by A1 plus U2 plus V2 multiply this one by A2 plus UN plus Vn multiply this by AN. So then we will distribute A1 there. So this is similar to U1 A1 plus V1 A1 plus U2 A2 plus V2 A2 plus plus UNAN plus VNAN. So again, when we collect the terms which are like, so this is same as U1 A1 plus U2 A2 plus UN AN plus V1 A1 plus V2 A2 plus VN AN. So if you take you use in one side, and then later on you come add the B, this like that. So finally, this is the same as now. This is like that, and that one is like that. Okay. So therefore, these are like now. This is now like multiplying A by U, and then plus multiplying this A by okay, and if we now multiply A and CU, and we say CU is that, then this is equals to CU1 A1 plus CU2 A2 plus CUN AN, which is the same as factoring out C here, and then multiplying U1 A1 plus C outside U2 A2 plus C outside UN A. Again, since C is common in each one of them, then this is similar to C U1 A1 plus U2 A2 plus UN A. And finally, this is the same as C, and this is like what? A, C, A. That is a 2. Any question after that? Okay, let's come to 1.4. And this is identity. What is the identity matrix? So the identity matrix, which you can write as IN. IN is an n by n matrix. It's an n by n matrix in which all the diagonal entries are equal to 1. And all the off diagonal entries are equal to 0. I.e., we can write this as 1 All these are zeros. 0, 1. All these are zeros. Then 0, 0, 0. All these are zeros up to the last one there, which is 1. So the diagonal entry, this diagonal here up to the last one here, are 1. The others are zeros. The others are zeros. The others are zeros. Now, if we multiply the matrix, which you can take this as example number 3, computes the matrix vector product in x, where x equals to x1 up to xn is in n. Then if we multiply in by the vector x, it is similar to getting now this 1, 0, 0, 0, this 0, 1, then all these are zeros, then this is 0, 0, 0, and all those are 0 to 1. Multiply this by x1, x2, up to xn. Then the product here, the product which we get is similar to multiplying this 1 by this by that by that, which is the first entry will be 1 by x1. And then all those entries plus the second one, which is 0, x2 plus 0, x3 plus 0, xn. Then and then the next one is 0, x1 plus 1, x2 plus 0, x3 plus 0, xn. The last one will be 0, x1 plus 0, x2 plus 1, xn. So what we get is equals to x1, x2, up to what? Xn. And this is similar to what? The vector x. So when you multiply the matrix, which is a linear matrix by a vector, then you still get the same. Okay, the same. Okay. That is it for today. So when we meet, then we can now come to the next section, which is matrix equation and linear system. Okay, I'll see you on Friday.